Every day, on every beach, waves rise and break. One wave always follows another. But did you ever wonder where waves come from? Why do waves seem to strike parallel to the shore? And why do they break when they approach the shore? We know that wind creates waves because on a day when the wind is not blowing, the water surface is often smooth. But on a windy day, there are always waves. The wind that pushes this sailboat also pushes the surface of the water and makes small waves. These huge waves, in contrast, were created by the gale winds of a great storm. Let's see how wind makes waves. This is a wave tank. It was designed for studying waves under controlled conditions. At one end is a powerful fan which blows air across the water. The tank has glass sides so that waves can be seen from the outside. Watch what happens when we turn on the fan. At first, the wind makes only small ripples on the water. As the wind continues, the waves grow larger. The longer the wind blows, the larger the waves become. Waves form when energy is transferred from the air to the water. Now let's speed up the fan. The waves grow even larger. We see that the harder the wind blows, the larger the waves become. Finally, the biggest waves are found at the very end of the tank, farthest away from where the wind first strikes the water. It seems that the greater the distance over which the wind blows, the larger the waves become. The wind blowing over this lake strikes the near side of the lake first and makes only small ripples. But on the far side, the same wind has produced much larger waves. All waves travel out from the area where they were created. They continue traveling until they meet an obstacle, in this case, the shore of the lake. So when we see waves at the beach where there is no wind blowing, it usually means that the waves have traveled from somewhere out at sea where the wind was blowing. Great storm waves like these are found where they're blowing for a long time, at high speeds, in the same direction, and over a long distance. Waves spread out from the storm centers where they are created and may travel for thousands of miles before they lose their energy or meet an obstacle, such as the shore. Waves on water are constantly traveling. But what about the water itself? Does it travel along with the waves? Let's observe what happens to this ball when we throw it into the water. The ball stays pretty much in place, even though the waves keep moving toward the beach. If the same ball is dropped into a river, it gets carried away. We see that an object floating on water will move as the water itself moves. Apparently, the wave form moves through the water, and the water itself stays pretty much in place. Let's do another experiment and find out how much the water in a wave does move. We'll use a wave tank again, but instead of using wind to make waves, we'll use a mechanical wave generator. The energy that makes these waves is provided by the regular movement of the wave generator. These simple waves are easier to study than the complex waves we find in the ocean. A small ball floating near the surface of the water behaves in much the same way as the larger ball did in the ocean. Let's watch it in slow motion. Each time the high point of the wave, called the crest, approaches the ball rises and moves forward with the wave. As the crest passes and the low point of the wave, called the trough, approaches, the ball moves down and backward. After each cycle, the ball is back to just about where it started. The motion of the ball is almost circular. This means that the water on which the ball is floating is moving in a similar circular orbit. At the water's surface, then, the effect of a wave is to make particles of water move in circular orbits. Now we can see what happens below the surface by putting weighted balls into the water. While the uppermost ball moves in an almost circular orbit, the deeper we go, the smaller the orbits become. The water moves less and less. Finally, at a certain depth, there is no measurable motion at all. If we measure the depth at which a wave no longer moves the water particles, we find that this depth is equal to about 1/2 the distance between two successive wave crests. This distance is called the wavelength. The deepest ball, which we don't see move, is at a depth greater than 1/2 a wavelength. The upper balls are less than 1/2 a wavelength deep. Now we know something about how water moves in a wave. But why do waves break as they approach the shore? This is a typical sandy beach at high tide. At low tide, we see that the beach is actually sloped. A wave breaks when it travels from deep water to shallow water. What else happens to waves as they move into shallow water? Looking from the air, we see that as waves approach the beach, their wavelengths get shorter. Notice that the distance between these two waves is greater than the distance between the next two. This must mean that the waves are slowing down and bunching up as they get closer to the shore. What is happening to the water particles within the waves? We have seen that most of the orbital motion in a wave takes place within 1/2 a wavelength of the surface. When the bottom of the tank, or the bottom of the ocean, slopes upward, at some point the water depth becomes less than 1/2 the wavelength of the wave. When this happens, the bottom interferes with the circular orbits of the water particles, and the orbits become flattened. Instead of moving in circles, the water moves back and forth. The wave is said to feel bottom, and it slows down. Meanwhile, the water particles closer to the surface are still orbiting quickly. As a wave moves into even shallower water, the wave form continues to slow down until a point is reached when the water particles in the crest are moving faster within their orbits than the wave is moving forward. When that happens, the water in the crest of the wave outruns the wave. The crest pitches forward and the wave breaks. A surfer riding a wave may not know it, but the reason his wave curls is because the orbital motion of the water has become faster than the wave itself. If you have watched waves roll into the shore, you may have noticed that waves almost always arrive parallel to the shoreline. Why do they do this? Since waves are produced by storms anywhere out at sea, they travel toward the coast from many different angles. But as waves get closer to the shore, they swing around until they are almost parallel to the shoreline. We can understand this if we remember that waves slow down as they move into shallow water. This means that when waves meet a shoreline at an angle, the part of the wave nearest the shore is slowed down first. In the meantime, the part of the wave that is still in deeper water continues to move forward at normal speed. It will not slow down until it too reaches shallow water. When one part of a wave moves faster than another part, the wave bends. This is called wave refraction. We can see waves refract as they enter this bay. The waves first feel bottom just in front of the headlands, where they slow down and break. The part of the wave traveling through the deep water continues onward at full speed. The result is that the waves bend toward the headlands and spread out in the bay. That's why the same waves that crash into the headlands break more gently in the bay. The natural waves we have studied so far are caused by wind energy being applied to the surface of the water. But what other ways are there to make waves on water? This is the lighthouse at Scotch Cap, Alaska, as it appeared before April 1st, 1946. Early on that morning, huge waves destroyed the lighthouse and a radio tower that stood over 100 feet above sea level. About 3 hours after the waves destroyed the lighthouse, similar waves caused this damage to the Hawaiian Islands, more than 2,000 miles from Alaska. On the coast of California, a tide measuring station in Crescent City was recording the normal rise and fall of the tides. At almost exactly the same time that the huge waves hit Hawaii, this station also recorded sudden large changes in sea level. In addition to these 3 locations, unusual waves were also recorded at several other tide measuring stations along the coast of North and South America. The farther away from Alaska each station was, the later the waves arrived at that station. From the speed and direction of the waves, scientists pinpointed the source of the waves to a small area of the Pacific Ocean off the coast of Alaska. The waves crossed the 2,200 miles of open ocean between Alaska and Hawaii in about 4.5 hours. By dividing the number of miles the waves traveled by the time it took them to cross the distance, we find that the waves must have traveled at an average speed of about 488 miles per hour. Wind could never have produced waves traveling so quickly because wave-generating winds never blow that fast. How were these giant waves created? One way to make a wave is to apply energy to the container holding the water. We know now that the waves that damaged Hawaii were seismic sea waves created by a strong earthquake off the coast of Alaska. The earthquake actually moved the floor of the Pacific Ocean. Seismic sea waves, also called tsunamis, contain more energy than ordinary waves because their energy is distributed throughout the entire depth of the ocean. In comparison, the energy of wind-driven waves is limited to the surface layer of the ocean. On the open ocean, the earthquake off Alaska produced seismic sea waves that were only a foot or two high and over 100 miles apart. These waves traveled harmlessly past ships at sea. However, when these waves moved into shallow water near Hawaii, all the energy that had been distributed in 12,000 feet of water was suddenly compressed. Ordinary waves were lifted to extreme heights and washed over dock and waterfront areas. In river mouths, the tsunami appeared as rapid changes in sea level, causing seawater to rush far upstream. In some places, the waves rose almost 40 feet above the normal water level and caused damage more than 1/4 of a mile inland. Fortunately, most waves do not carry enough energy to do much damage. Seismic listening stations rimming the Pacific now give early warning of potential tsunamis. But all waves do carry some energy, and most of it is released against the shore, and sometimes in a wild ride down a wave.